So we're going to be doing problem 2, the first step of it. So let's write down our heat diffusion equation. So d of temperature over d of T is equal to alpha, the second derivative of temperature, temperature over delta x. So what this is saying is that um, it's relating temperature as a function of time with the temperature as a position of x as it moves forward. So what that means is that we have our bar, right? And we'll split it up into, let's just say, this many parts. So we got 1, 2, or more likely 0, 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 segments of this bar, and we want to take the temperature, this term, we'll take the temperature at each of these points, right? And then this one will take it at however many time steps we have, and we'll keep on doing that array. So how do we write? We have to expand this form because we can't do that. So we know we have to do TJN, this notation, where the N represents time and the J represents the position. So let's expand this out. So we need the time to the left, so n plus 1, minus the time to the right of it, all over delta t. We need to set that equal to the alpha value, and then it's the derivative of the derivative. So let's just write out the first part of it. Oh, that needs to be, that cannot be that, it's d squared of x. So in this first part, it is tj plus 1n minus tj over delta x, and then it's the derivative of that. So we need the tj n minus tj minus 1n over delta x. We subtract that, and that's all over delta x, because it's a change in the slope of the change of the slope. It's the second derivative. That's what that means. So let's simplify those. So it's tj plus 1n minus 2tjn minus tj minus 1n all over delta x squared. So we plug this back in to this top equation. We'll write it in orange. So tjn plus 1 minus tjn over delta t is equal to the alpha of tj plus 1n minus 2tjn minus tj minus 1n all over delta x squared. So we need to get this term alone. So how do we do that? We just do some algebra. So tjn plus 1 minus tjn is equal to alpha delta t over x delta x squared, then tj plus 1n minus 2tj jn minus tj minus 1n. And then we just add this to the other side. So tjn plus 1 is equal to tjn plus this term will just cancel out into an r value. R tj plus 1n minus 2tjn minus tj minus 1n. And that is our final equation that we need for this to solve the code, and we'll move to that right now. All right, let's move on to the coding portion of this assignment. there. Okay. So first we need to import numpy as np. Then it is from plot e. Make sure that worked. Alright, so now we need our time steps. We're going to define that as nx. We're going to set it equal to 100, and then our time steps, denote as ts, is equal to, let's just say 200. And then the r value that is given to us is 0.1. So we need to make an array of our temperatures of our bar. So how we do that is we set t is equal to np dot full, and then we say its dimensions are nx, and then its fill is 300 dot. Oops. And then it is then at the very right side of it, the initial temperature of it is 350 degrees Kelvin. Oop, need to do T0 is equal to 350 Kelvin, and then stop. Nope. Okay, then its left side, so we'll denote that as -1, goes to 400. Okay, then we need an x value if we're going to make a plot. So we say x is equal to np dot range nx. So if we plot x, it is defined. Excuse me. Alright, then shift enter. Just gives us a number from 0 to 99. So that's good. So we need to do fig is equal to make subplots rows is equal to 1, columns is equal to 2. And then fig dot add, what is it? T, and that should have popped up. We'll see what's wrong. Mode is equal to lines. Name is equal to initial. Then we do our time steps for I in range of 1 comma ts plus 1. And this is the confusing part. It's t1 colon -1 is equal to t1 colon -1. plus, let's be outside, plus our R value times, and in parentheses, T2 colon minus 2 times T colon, what is it, -1, then minus T bracket colon -2. If I percent 1000 y is equal to T mode is equal to lines name is equal to F I. Oh, that second bracket. Okay, then we do fig show. We should get a nice, oh, okay. So now we have a nice graph here. Put this in its own little parentheses, because that's not what the graph is supposed to look like. Hold on a second. Alright, I found the mistake, and it's right in here. That needs to be a plus sign instead of a minus. No, that is still not right. Here, let's move these in its own parentheses. See if that makes the difference, and it doesn't. 1 second. Alright, I have found the issue. The issue was that there was a space in between here and there, causing that for statement to not function properly. So we just wait for that to complete. So there's no lines on this graph. You see, it's trying to do something, but it's really not going at it. Let's try to make that smaller. There we go. Alright, we can see it's starting to make some sort of a graph. But let's play around with this R value. Let's say it's 0.4 this time. And we can see it's slowly coming up. Let's do 4.999. And you can see it's getting there. Let's do more time steps. So add a couple more zeros to that. And then we're going to add a hard. And look at that. That's a nice looking graph. Now what happens if we plug in 5 for our R value, 0.5%? Okay, this still works. What about 5.5? We're getting numbers all the way up into times 10 to the 234th. So that can't be right. So when we return, we'll be discussing on why this version of finite differencing isn't good for arbitrary values of r greater than 0.5. Alright, so now let's prove why we can't have an r value greater than 0.5. So we know, let's recall the Euler equation. Is equal to e to the ix is equal to cosine of x minus I sine, or I plus sine of x. Then e to the negative ix is equal to cosine x minus I sine of x. And what we're going to prove in this von Neumann stability analysis is that t is equal to e to the ikx, then e to the negative alpha k squared t. And we're going to plug this in. We're going to prove that we can get to here from there and there from here. So we're going to write out our heat diffusion equation. dt is equal to alpha e squared, so t over d of x squared. And we're just going to plug in this t value into both of these t's. Right there. So let's write this in blue. I like blue. So what we do is we have to take the derivative to dt in this. So it is negative alpha k squared t e to the ikx e to the negative alpha k squared of t is equal to alpha. We have to take the second derivative of these. So it is ik squared. I squared is I. Alright, so today we're going to be doing the von Neumann stability analysis for this function. So first let's pull out our Euler equation. That just states that e to the ix is equal to cosine x plus I sine of x. And then e to the negative ix is equal to cosine x minus I sine of x. Now, to make our life simpler, we want to prove, firstly, that t is equal to e to the ikx e to the negative alpha k squared t. So how do we do that? We plug it into our heat diffusion equation, which, to remind us, looks like such. D, the change in temperature over the change in time, is equal to this alpha value, change the second derivative of the temperature over the change in x. So we plug in this to both of these t values and take the derivative as such. So on the left-hand side, we get negative alpha k squared e to the ikx e to the negative alpha k squared t. And that's all equal to the negative alpha, and then the second derivative on that side. So it's I squared k squared e to the ikx e to the negative alpha
k squared t. And we can see that both of those two equations are equal to each other, so we have proven that that is true. So just move on. So now we have to pull out our Fourier series. So our Fouriers, or Fouriers, is how temperature is equal to the sum of the k to infinity to negative infinity of ck, and then this equation, e to the I kx, e to the negative alpha k squared, right? Yeah, t. So what we can do is now we can put that into the form of this. There's supposed to be a j there. Form of that. So t to the jn is equal to e to the ikj delta x, e to the negative alpha k squared n delta t. So having that, where do we go from here? Well, we can plug into this top equation up here, and we can factor out these plus ones and minus ones to make our lives a little bit more simpler. So let's do that. We're going to do it a new color. We're going to do green. So tjn plus 1 is equal to tjn plus r times tj plus 1n minus 2tjn plus tj minus 1n. So how do we plug in, or what plugs in to make these simpler? Well, we do the tj plus 1 is actually equal to tjn e to the ikx. Okay? And then inversely, the tj minus 1n is equal to tjn e to the negative ikx. So let's plug that in. T to the j n plus 1 is equal to tj n plus r brackets e to the ikx tj n minus 2t j n plus t j n e to the negative ikx. Now, after you simplify all of this, you actually end up with something that looks pretty nice. So tj n plus 1 is equal to tjn times 1 plus, it's r 2 cosine of k delta x minus 2. Wow. So, what does that mean for us? Well, what we can do is firstly, we can factor out a 2 in here. So 1 plus 2r cosine of k delta x minus 1. So we know that this whole equation, hold on, I'm missing something. Okay, it's actually correct, surprisingly. So we know that these values right here have to be between negative 1 and then 1. And if we subtract 1 out from it, we get, it has to be our new bounds. We're at negative 2 and 0, right? So we write this inequality out. Negative 2 is less than 2r cosine cosine of k delta x minus 1 is less than 0. Divide by 2 on both sides, we get negative 1 r cosine of k delta x minus 1, 0. And now we have to look at this part. We know that at least cosine is between negative 1 and 1, right? We subtract 1 from that, and we get cosine is now between between negative 2 and 0. So we write that inequality out as negative 1 to r less than 0. This side we don't really care about. And we divide by negative 2, divide by negative 2, and then we get r has to be less than 1/2. And doing this, we have proved the von Neumann stability analysis on this problem, and this shows why the r value can't exceed 1/2.